This is the Sun. Located more than 93 million miles away, it is the closest and most important star for us humans. Today, we're going to learn more about it by investigating its internal structure. We'll accomplish this by creating a C++ simulation to model a set of differential equations that give us the density, pressure, and temperature at different depths within the Sun. Once we do that, we'll be able to create stunning visualizations of our data. Our simulation will work by dividing the Sun into 500 concentric shells. Each shell will be treated as uniform and homogeneous throughout, making it easier for when we need to solve our differential equations. Of course, this isn't accurate to the actual Sun, as each shell will be non-uniform, but the assumption works well enough for our purposes. We'll solve each differential equation numerically using Euler's method. Euler lets us calculate the change in a specific property over each shell. We can then take that change and add it to the last shell, and continue this process until we know the values of all shells. As long as we know the properties of one shell, we can start from there and solve the properties of all the other shells. For simplicity reasons, we'll start from the central core shell. Before we actually simulate this data, it's important to have a way to visualize it. Now, since we are working in C++, it's entirely possible to use libraries like Matplotlib or OpenGL. However, it's kind of annoying to use C++ for visualizations, so I wrote a quick Python program that uses Matplotlib to make plots of our data. Each plot will analyze how a specific property changes at different radii in the Sun. We'll store our C++ simulation data into a CSV file that the Python program can then access. We'll then store our plots into a folder named profiles. If you would like access to the plots or the code, check out the Github repository in the description. Let's now look at how we're going to simulate this data. We're going to use Euler's method to solve 4 differential equations. I'll cover them generally so that we can get a gist of what they mean, but if you would like more detailed derivations and explanations, I've attached a couple links in the description. The first one explains the pressure gradient. We obtained this equation from that of hydrostatic equilibrium. Pretty much, hydrostatic equilibrium just says that the pressure pushing up from the Sun's core has to equal that of gravity pulling down to the core. Knowing that, we set the gravitational force and the force and pressure equal to each other, and some algebra gives us this equation. The second one gives the mass of each shell. We can imagine our shell as having some volume 4 pi r squared dr, because the surface area of the shell is 4 pi r squared and its thickness is dr. We then multiply this by the density of the shell to get its mass. The third one explains the temperature gradient. I'll spare you the math, but it's important to note that there are technically 2 equations for this. The first one assumes that all of the energy being transferred out is radiative or electromagnetic in nature. It's important to note that this equation is dependent on a value known as the opacity of the Sun, which basically describes how hard it is for heat to travel through the Sun at different shells. The second one assumes that all of the energy transport is convective, meaning that energy is transferred to the movement of the fluid. In reality, the Sun switches from mainly radiative transport to mainly convective transport in the outer 30% of its volume, but we'll be simplifying our model by assuming that the Sun stays radiative throughout. Last but not least is our fourth equation, showing how the luminosity of the Sun changes throughout different shells. If you'll notice, it's very similar to the differential equation of the mass with the addition of this epsilon term. This is called the energy generation rate, and it shows how much energy is being generated per kilogram of mass in the Sun. Now, we need to have equations of state for our density, opacity, and energy generation rate. These values are going to be dependent on our pressure, temperature, and composition of the Sun. We use a version of the ideal gas law for density, Cramer's law to approximate opacity, and a similar power law approximation for the energy generation rate. Let's now talk about the code. I started this project by writing a shell structure. In C++, a structure basically allows you to store a bunch of properties for any object. In our case, that involves storing the radius, energy generation rate, opacity, mass, luminosity, pressure, temperature, and density at that shell. I then created a Sun class. C++ classes are similar to structures, but they're also better for when we actually want to do things with our data. In our case, we want the class to store a list of our shells. In our constructor method, which runs whenever we create a new Sun object, we initialize all of the shells with a default value except for the first shell, which we initialize with our known core constants. I then created another method which would run the simulation. Pretty much, it loops through each cell in the list from the core outwards. It updates the current shell's properties using the Euler's method and the last shell's properties. It calculates the differential equations using methods I defined in another file. In our main file, I wrote a quick method which would write all the data to the CSV file. In the main program, I created a new Sun, ran the simulation, and called the write method. Okay, let's see the results. Oh dear. I don't think the temperature is supposed to go negative. I think what happened here was that small errors in our calculations compounded, and this led to wildly inaccurate results, which led to our C++ code being unable to calculate further. Let's fix this by capping the values for our methods at an incredibly small, positive number. After all, we know that temperature and pressure continuously decrease in the sun, and the luminosity and mass continuously increase. Therefore, we know something bad happened if they go in the opposite direction. Let's run it again. Okay, at least our temperature didn't go negative this time, but there's definitely still a problem here. The sun's temperature definitely does not go to absolute zero at 10% of its radius. So what's the issue? Well, remember how I mentioned earlier that we needed equations of state for the density, opacity, and energy generation rate? We actually use approximations for these values in our code. Now, approximations are great, but they can provide a whole lot of error that introduces issues into our simulations. For proper solar models, there are a plethora of datasets that allow you to get these values for various temperatures, pressures, and chemical compositions. The downside is that we would now have to simulate how the chemical composition of the sun changes to actually use these datasets. But we actually don't need to worry about opacity at all. Let's see how we can study the internal structure of the sun by looking at the Eddington solar model. In the 1920s, Sir Arthur Eddington wanted to study the internal structure of stars. Like us, he was also faced with the problem of opacity, with the only difference being that he didn't have access to those aforementioned databases. However, he was still able to develop a model that can analyze the sun. We call this the Eddington solar model, and we will be using it for our simulation. I'll spare you most of the math, but if you are interested, I would highly recommend checking out Dr. Richard Fitzpatrick's notes that are linked in the description. Pretty much all we need to know is that there are two equations that we can model. The first is called the Lane-Ambient equation, and it relates a dimensionless radial coordinate with a dimensionless temperature constant. The second equation relates a dimensional mass to a dimensionless temperature. The key insight is that our dimensionless values are directly proportional to their non-dimensional counterparts, and our dimensional temperature can be raised to different powers to obtain our pressure, density, and temperature. Those constants of proportionality you see there are our core values, so we will be simulating from the surface inward. The only thing missing is our luminosity and mass. In this case, we can simulate the pressure, temperature, and density from the surface down, and then go again from the core up to simulate the mass, energy generation rate, and luminosity using the old equations but with the predefined pressures, temperatures, and densities. Okay, let's run the simulations. Hey, our graphs look great. We now have a working simulation for the internal structure of our sun. Now, up until now, we were using Euler's method to solve our differential equations. This is okay, but it does provide a non-significant amount of error. There are, in fact, other ways to numerically solve differential equations that are actually significantly better. The most known of these is known as Runge-Kutta 4, or RK4 for short. It basically works by simulating 4 steps ahead, and then taking a weighted average of those 4 steps that favor the 2 middle steps. Again, check out the description if you're more interested in the math behind it. So, let's write an RK4 simulation of the Eddington solar model and run it. Okay, so it definitely worked, but something's clearly wrong. The luminosity of the sun is around 3.8 times 10 to the 26 watts. Euler's model simulated 2.5 times 10 to the 26 watts, but the RK4 one is somehow more inaccurate at 2.3 times 10 to the 26 watts. So, what's going on here? Well, the issue is actually that our model under-approximates luminosity because of error within the model itself. The Euler simulation is only better because of the error involved with solving with Euler, but the RK4 one solves the incorrect model better, leading to a more inaccurate result. With that out of the way, we can now make a visualization for our data. Using Pygame, I created a window that drew 500 concentric circles. I used Matplotlib to create a color map for each property, where the color corresponds to the ratio of the property's value at that radius to the property's maximum value. I also drew 3 reference circles to show where the core, radiative zone, and convective zone were. We now get a nice visual that accompanies our simulated data, finishing our project. The visuals help us picture exactly what is happening in the sun. For example, the energy generation rate visually shows us that nearly all the energy generation in the sun is happening in its core. That doesn't mean that our work is done, however. Looking back to the core values for our Eddington model, we see that they're actually fairly inaccurate because the model makes so many sweeping assumptions. We also don't see a change in our profiles once the convective energy transfer begins because the Eddington model assumes the sun is fully radiative. These problems go away if we account for opacity using the databases I talked about earlier, so it should make for a good future project to simulate the standard model and compare it to the Eddington model. For now, however, that will have to be all. If you are interested in the project, I encourage you to check out the GitHub link below. From the bottom of my heart, thank you so much for watching.